Hello, this is Mrs. Nearing, and we're going to look at one problem here where we consider both calorimetry during a temperature change and also the energy changes that occur during a phase change. So if you remember looking at maybe a heating or cooling curve like this from maybe regular chemistry, we had temperature on the y-axis and the amount of heat added on the x-axis. And you see that what happens is as you add heat to, let's say, a sample of liquid water, we would see the temperature rise as you added heat. Once you hit a certain temperature here, like in this case it would be 100 degrees Celsius if we're looking at water, then we would see it flatten out for a while as you add heat. So you're adding heat, but the temperature is not increasing. And so the heat must be going somewhere else. And what that heat is doing is it is being involved in a phase change. So in these kind of heating or cooling curves, we will see these flat parts where phase changes occur. And so any energy being added here is going into changing the liquid water into gaseous water. And that occurs at a constant temperature because the energy added is going into basically changing the potential energy rather than the kinetic energy. So as you change temperature, you are changing the kinetic energy of a sample. And as you change phase, you are changing essentially the potential energy, the position of the molecules within a sample. So once you go through that phase change and everything becomes a gas, then as you keep adding energy, the temperature of the gas would start to increase again. So we're going to kind of look at the interplay here between looking at temperature changing and phase changing, and we're going to try and figure out how much energy it takes to melt some ice. So if we look at this setup here, you have a block of ice, and this is 1 mole of ice, and it's at 0 degrees Celsius. And never mind. We're trying to figure out how much energy it takes to melt 1 mole of ice. So what is our actual sample size? Okay, we have our sample size of ice. I was thinking that was a weird number. Okay, we have 9.68 grams of ice, and it's at 0 degrees Celsius. Okay, and it's added to a calorimeter containing 278.3 milliliters of water. And the temperature of the water beforehand is 22.48 degrees Celsius. And so when you put this ice in the water, we know that energy is going to go from the higher temperature object to the lower temperature object. So energy is going to flow from the water into the ice. Okay, and as it does that, the temperature of the water is going to decrease because it looks like the water is going to be losing energy to the ice. The final temperature of the water is going to be 19.04 degrees Celsius. So it looks like the water is going to be losing heat because it's going to be giving its heat to the ice. And we can find out how much energy the water lost by using calorimetry because we got a temperature change happening. So we can use this equation, Q equals mc delta T. Okay, so the mass of the water is 278.43 grams, because again, this isn't written here, I think is written at the top of the page, that we're assuming the density of the solution is 1 gram per milliliter. So that means if you have 278.3 milliliters, that would be 278.3 grams. You would have to be given that, assumption somewhere in the problem. It'll say assume the density of the solution is this. Okay, so that is our mass. Our specific heat, again, earlier it says to assume the specific heat is the same as that of pure water. Well, never mind, this is pure water. So the specific heat of pure water is 4.18 joules per gram degree Celsius. No, you don't need to memorize it. It will be given somewhere in the problem. So this is 4.18 joules per gram degree Celsius. And then the temperature change is final minus initial, so 19.04 minus 22.48. And that is getting a little messy there. So if we plug that in my calculator, 19.04 minus 22.48, we can see the temperature change is negative 3.44. Okay, so we stop and plug that in your calculator. It's negative 3.44 times 4.18 times 278.43. Okay, so it looks like the water is losing 4,003 joules of energy. If I wanted to write this with 3 sig figs, this is one of those ones that would be tricky. So if I rounded it to negative 4,000 joules, that would only have 1 sig fig. If I put a decimal at the end, that would be 4 sig figs. So if I wanted to write it with 3 sig figs, I would have to do something like this. Negative 4.00 times 10 to the third. That would give me 3 sig figs. FYI. Okay. Now I want to find the amount of heat absorbed by the ice after it melted. So what's going to happen to the ice is 2 things are happening here. It is starting, if we draw our kind of a heating cooling curve right here, imagine that we start at 0 degrees. As you add heat to the ice, at first the temperature is going to stay the same as the ice melts, turns from a solid into a liquid. Then once it becomes a liquid, the temperature is going to increase. And in our case, it increases until it reaches 19.04. That's the point at which our system has reached what we call thermal equilibrium. And that is the point at which the temperatures are equal and the energy stops flowing. So we put the ice in the water, the system reaches thermal equilibrium, our final temperature was 19.04. Okay, so we're going to figure out how much energy was absorbed during this section of time. So that's when you have, the ice is already melted, so now it's a liquid. So the specific heat of liquid water is 4.18 joules per gram degree Celsius. And then the mass of our ice was 9.68 grams. So to find Q, our mass is 9.68 grams. Specific heat is 4.18 joules per gram degree Celsius. And the temperature change is 19.04 minus 0. Okay, so let's plug that in your calculator. 9.68 times 4.18 times 19.04, and you end up getting 770, not grams, whoops, this is joules. Okay, so that's how much energy was absorbed when turning your liquid ice at 0 degrees into the liquid at 19 degrees. Okay, so now let's figure out how much energy it takes to do the actual melting, and that's kind of the purpose of this experiment. So this is an experiment we could do in the lab, is we could figure out how much energy was absorbed turning that solid ice into liquid ice at 0 degrees. So what we know is the amount of the energy lost by the water is going to be equal to the energy gained by the ice. And we know that the energy gained by the ice went to 2 different places. There was the energy to melt the ice, and there was the energy to heat the melted ice from 0 to 19 degrees. Okay, so the energy lost by water, we found that out in problem A, and maybe I'll stop worrying about sig figs here. We'll just kind of put in 4,003 joules. That's the energy lost by the water. The energy required to heat the melted ice was 770. So we should be able to figure out how much energy it took to melt the ice. Yeah. And let's not worry about the sign here. Or I should put, this should be negative. It would be negative of a negative. So it would end up being positive 4,003. Okay. So the, let me clarify that here. So it's going to be negative 4,003. So it's actually going to be positive 4,003 joules. That's why I got rid of my negative sign over there. All right, so it's 4,003 joules minus 770 joules is going to be how much energy was needed to melt. That's the energy required to go through that phase change. And we can't find this out directly through calorimetry because phase changes don't involve a change in temperature. So we have to kind of have an experimental setup like this to figure out how much energy went into the actual phase change part of this. So if you look 4,003 minus 770, it looks like it took 3,233 joules of energy to change the phase, which means change the ice from solid ice to liquid ice. So let's find that in kilojoules per mole. So I'm going to convert my joules into kilojoules. That becomes 3.23 kilojoules. I think I had 3 sig figs there. And I'm divided by moles of ice. So my sample of ice was 9.68 grams. And remember, ice is water. So 1 mole of water weighs like 18.01 grams here. So you end up with 9.68 divided by 18.01. So that's 3.23 kilojoules divided by 0.537 moles. So 3.23 divided by 0.537. So that's basically 6.01 kilojoules per mole. So what that's called is, this is called the heat of fusion. And that is the energy to change phase from solid to liquid. So remember, that phase change requires energy, but it will not result in a temperature change. All right, thanks for listening.